As you know, there's going to be air drag. As any object moves through the atmosphere, there's going to be some drag put on the object, which is the friction between the air and the object, and that slows it down. If you assume that the velocity of the object, technically you talk about the Reynolds number, but that's not that important. If you assume that the velocity is small compared to the size of the object and so on, the force, the drag force, is going to be proportional to the velocity of the object. Okay? So laminar, I think you did that in the lab, right? Dropping steel ball bearings and seeing what's the thermal speed. So if you assume that the drag force is proportional to the velocity, then the motion of this object is going to be simple harmonic motion, and you add a term that is going to be minus e, some constant times the velocity. So what that term, drag, is going to do is going to slow down the motion of the object. So the amplitude is going to decrease, little by little is going to decrease. If this was moving through molasses, it would decrease extremely fast. Like in air, it just takes some time depending on the size of the object. But eventually it's going to end at the equilibrium point. Right? So what are the equations, or how does the object behave when that is the case, when you have a non-negligible drag force? So what we have here, this, as I said, you can find it in null space. I'll make it, I'll tell you exactly where, and it's very visible, so you can play with it. So you have some parameter here, strength of the drag force. If P is 0, then there is no drag force. And if you set those values, and you pull this object, which is attached to a spring, then you know what it does. What this is plotting is the position with respect to the equilibrium point as a function of time. So it describes a cosine function, right? And the amplitude is constant. Without drag, it will keep doing this forever. So now what happens when you add some drag? Didn't quite reach the original amplitude, which was 10, right? In the second, when it completed one oscillation, it was maybe at 9, and it keeps going down. So let's look at what kind of equation will describe this sort of behavior that you're seeing there. The object is still oscillating nicely, as a sine or cosine curve, but the amplitude is going down. It looks like it's exponentially going down. The envelope, if you connect all the peaks, right, and you draw a line connecting all the peaks, it looks like it's an exponential. It goes down. So Newton's second law is F equals ma, or the problem where there is harmonic oscillator, that is, for example, a block attached to a string, but there is also drag. Then it will be like this. The forces are going to be spring force, and then on top of that you have minus some constant here that determines, that has to do with how much air drag there is, times the velocity of the object, and that should be the mass times the acceleration of the object. Without this, as we said, that equation we have already solved. It's a simple harmonic oscillator, and we have the answer. Right? With this, the solution looks like this. Position as a function of time. We will have oscillations. So there is a cosine here, so the usual omega t plus phase. But here you have an exponential decrease in the amplitude of the oscillation. So the amount of damping that you have, V, shows up here. The mass of the object is there. And this function, as you know, is exponential, which means that if you look at this as the overall amplitude of the motion, that amplitude is a function of time. And it starts with some amplitude at the beginning, and that amplitude goes down, decays. And that's exactly what you were observing in that plot. The line that you draw connecting all the peaks, that line is the amplitude, and it decays exponentially. There is a modification of the frequency of the oscillation due to the damping. The new frequency is the frequency without damping, which is square root of Km. But there is something else inside the square root. V squared over 4m. I'm not going to do any of the details of showing that this is a solution of that equation. Just trust me that that's the answer. And this is how the frequency is modified by the damping. Okay? We can write this as square root of omega 0 squared minus v squared over 4m squared. That's just writing the same thing, just calling this quantity the angular frequency without any damping. So you can see that whenever there is damping, the angular frequency is going to be smaller than the frequency without damping. Sort of makes sense, right? Think of this pendulum as moving through molasses. What is the effect of the molasses on the frequency of this thing? It's going to slow it down quite a bit, right? It might be one oscillation and a half, and it will stop and so on. But that frequency is definitely going to be stretched. It's going to be smaller, which means the period is going to be longer, right? If you have damping. There's also something very interesting from this equation that you can see from this equation. What happens when this term is as big as this? What's going to happen? See, typically for the pendulum that we have there, this term is much smaller than this. So you have the oscillations last for a while, right? That's when this is small. But what happens when the damping goes up so much that it matches this? The frequency of the angular frequency of the oscillations goes to 0, which means the period goes to infinity. So the motion of the object is very slow. It goes very slowly towards the equilibrium point, and that is called critically damped. Starting from some initial amplitude, and it just goes toward the equilibrium point. It's actually the fastest way to make an object go towards the equilibrium. This is actually important, for example, in the shock absorbers of your car. The setup there is a spring. So if you go over a pothole, the tire will move down and then up, right, to the bottom of the pothole, and then it's going to be kicked back up. And if that was a rigid support, the car would feel that the force of that impact pretty strongly, right? So you want to have something that buffers that. So people put a spring there. The problem with just a spring is that your car, after you go through the pothole, will keep moving like this, right? So you have to put some sort of mechanism that makes those oscillations of the car go down, and you want them to go down as quickly as possible. You don't want the car to keep bouncing up and down for a couple of miles. So the damping is the shock absorber. It has a fluid inside, and things have been designed in such a way that the B introduced by the damping of the shock absorber, this term matches the natural frequency of the car because of the springs that you put. Those two numbers match each other, and the car goes down to equilibrium quickly. Then under damp, we saw that, which is when the damping is small, so you have lots of oscillations, and the amplitude slowly goes down to 0, so very slowly. And the overdamp is when you have so much damping that this term is actually bigger than this one. If this term is bigger than this one, the angular frequency is not a real number. That means there is no oscillations. It actually goes exponentially down. The amplitude, the location of the object goes towards equilibrium in an exponential fashion. But it's actually turned out to be slower than the critical damped case. So there's no trace of any oscillation pattern. Takes a long time. Like I said, it's like putting this pendulum through molasses. It will definitely end up here at the equilibrium, but it's going to take a while. Very long time to reach that point. So that's what's happening with that problem. It's heading towards zero, but very slow. All right?